Welcome to the Business Talk, a global podcast series that highlights distinguished faculty members and their impactful scholarly contributions. I'm Deepak, your host from India. We are honored to welcome Dr. John Colin Mutter as our distinguished guest on Business Talk today. Before we get started, I would like to introduce today's guest. At the intersection of the Earth's geology and the world's deepest inequalities stands Professor John C. Mutter, a scientist who began his career listening to the ocean floor and now dedicates his work to amplifying the voices of those most silenced by disaster. A professor at Columbia University with the dual appointments in the Department of Earth and Environmental Sciences and the School of International and Public Affairs. Dr. Mutter brings a rare cross-disciplinary lens to some of the most pressing questions of our time. Why do natural disasters devastate the poor far more than the rich? And is that by accident or by design? His specialty began in marine seismology and science of reading seismic waves beneath the sea. But over the decades, his gaze shifted from tectonic plates to power structures. As the former deputy director of the Columbia Earth Institute under Dr. Jeffrey Sachs, he helped shape one of the world's foremost sustainability research institutions. Today, Dr. Mutter directs the PhD in Sustainable Development at the School of International and Public Affairs and teaches landmark courses including Environmental Science for Sustainable Development and Climate Change, Development and Human Rights. His research examines whether the outcomes of catastrophic events from Hurricane Katrina to 2010 Haiti earthquake are shaped less by the fury of nature and more by the failures of governance, inequality, and neglected human rights. He is the author of The Disaster Profiteers: How Natural Disasters Make the Rich Richer and the Poor Even Poorer, and most recently co-authored Disasters and Development with economist Dr. Sonali Deraingala of University of College London, a book born directly from the course they co-teach at Columbia. His Climate Change Science, a primer for sustainable development, published by Columbia University Press, now in its second edition, has become an essential resource for students engaging with climate systems from a policy and development perspective. Dr. Mutter's work is a reminder that behind every disaster statistic is a policy choice, and that science, when paired with justice, become a tool for transformation. In today's episode, Dr. John Colin Mutter joins us to explore the core ideas from his acclaimed book, Climate Change Science, a primer for sustainable development. Let's not keep you waiting. Please join me in welcoming Professor John Colin Mutter to the conversation. Professor John, it's a distinct privilege to welcome you to Business Talk. We are grateful to you for accepting our invitation.
No problem. Thank you. I'm
Thank you.
pleased to be here.
Thank you. Professor, your book is described as a just the facts primer. Yet, climate science is one of the most contested topics in public discourse. How do you draw the line between presenting objective science and addressing the deeply political atmosphere in which this science is now received?
Yeah, so this book came about as a way of trying to help students understand what is essential to know before, in terms of the physical processes, before they enter what is inevitably a policy or even political argument. So what I've written down here is what I think is the essential science that a person should know, even if they're not scientists. This is what you need to know to be able to be a sensible contributor to all the debates around climate change, whether they're, what should policies be, what are the political issues, and how they change so quickly. So it is really, there's no opinions in this book. I don't I don't express my opinion. I work from the fact that my early training is in physics, so I cannot help myself but look at the climate problem first as a physics problem. Now I know it's not just a physics problem, but there is a physics problem in the middle of this. And then there is a policy problem, and the IPCC has tried to deal with the policy issues. They provide a summary for policymakers, I'm not sure how often policymakers actually pay attention, but at least they make the effort. But then, of course, it's a political problem. It depends how the leadership of different countries view the nature of the problem, or whether they think it's a problem or not. And clearly, unfortunately, our current president in the United States, he doesn't think it's a problem at all. And he'd rather we didn't even talk about it. And he really doesn't want us to make any progress with the science. So that's most unfortunate. Um, I'm now very disheartened about the American attitude in the Biden administration. I used to think that the reasons for being optimistic were about equal to the reasons for being pessimistic. And now I'm completely pessimistic because it's hard in the US at least to have any positive feelings about the climate change problem and how it's being addressed by the leadership of the country.
Professor, you trace the history of climatology from its earliest discoveries to today's predictability capabilities. What was the single most transformative moment, a discovery, an observation, or a measurement that fundamentally changed how scientists understand how Earth's climate works?
Yes, let me try to think. So what I tried to do was give you the essence, um, and in particular, I wanted people to understand what the uncertainties are, and there are real uncertainties, and whether those uncertainties, where are they derived? Why is it uncertain? If it's a physics problem, somehow we'll figure it out. Physics problems always get figured out. Can take a while, but we get to the end when we found the Higgs boson after years and years, and that problem was solved. But if it's more than a physics problem, and it is more than a physics problem, it becomes very complicated. So we need to understand where the uncertainties come from, and I can explain it if you like, whether they're going to be resolved in this case, and how long it will take for them to be resolved. And after that, if they're resolved, if the physics problem is cleaned up, will anybody pay attention? And I'm almost completely certain that Donald Trump will not pay any attention. He doesn't believe in science. He's trying to suppress science by uh, slashing the Science Foundation's budget. Everything to do with science is being greatly reduced. Um, so it's a three-dimensional problem. It's a physics problem, it's a policy problem, and it's a political problem.
Professor, sea level rise is often treated as a slow, distant threat, something for future generations. But your book makes the science immediate. At what point does sea level rise cross from being a scientific concern to an existential civilization crisis? And are we already past that threshold?
So one thing to know about sea level is that it's not level. The sea level is at a different level in different parts of the world. So in some parts of the world, sea level is rising very, very slowly, almost not rising. And in some parts of the world, it's actually falling. Adjacent to the island of Greenland, sea level is actually falling. And that's because the ice is melting and it's not attracting the water towards it as it used to do. So it's actually falling. And science can tell us that. So I can make you a map, or a map can be made by scientists that shows you exactly where sea level is rising, how fast it's rising, and what a projection is for the future. So in a sense, you think of all the islands, particularly in the Pacific, uh, that are threatened by sea level rise. Well, some are more immediately threatened than others. Some are going to be in big trouble quite soon, and some will not. And science can tell us that. So that at least can give us some sense of priority. Which islands are in the most trouble? And the problem with our islands, uh, particularly those Pacific islands, is that very often they're relatively poor. They don't have any opportunity to create national wealth. They basically live on tourism, sometimes offshore banking, but they don't manufacture anything. There's no serious agricultural industry because the islands are too small. So they're very precarious. And if they need to be saved, and I'm not quite sure what I mean by saved from sea level, we can't stop the sea level from rising, but we might be able to do something to make sure that little islands are not harmed. But there are too many islands for the international community to save them all. There are 11,000 islands with humans inhabiting them. We cannot possibly save 11,000 islands. That's just too many. So we're going to have to think about which ones would come first. Okay. Well, science can tell you which ones are in the most trouble. And I try to detail that in the book. So it's one of the things I think everybody should know is the nature of the sea level issue, because it gets talked about a lot. Uh, and it gets talked about wrongly a lot of time.
Professor, you examine how rising temperatures affect hurricane behavior. Is the relationship between climate change and hurricanes now settled science, or is it still one of the most hotly debated areas of climate prediction?
So when you think of uh, tropical cyclones, there's two things to think about. Um, where hurricanes form, that is where they get started, and where will they go? So the second part of this, it's likely that the forces that control the track of a hurricane are going to be much the same. So most of the Atlantic hurricanes initiated off the coast of Africa, and they go from east to west across the Atlantic, and then some of them come ashore. That east to west motion is likely to stay the same, okay? But the water they encounter on the way is going to get warmer and warmer. And what cyclones need for their fuel is warm water. So the likelihood is that cyclones in the future will be stronger. However, the second issue is, how do they get started? The conditions going to change in the region where they get started. So will there be more hurricanes or fewer hurricanes? Okay. So what everybody thinks is that there's likely to be fewer hurricanes. So, but the issue is that although there will be fewer, more of them will be very intense. So you could think of it this way. If right now in the Atlantic Ocean, there are about 10 hurricanes every season, and about two of them become very, very strong. In the future, it won't be 10, it might be 8. But of the 8, 3 or 4 of them will be very intense. So the number of intense hurricanes will increase, but the number of hurricanes overall may not increase. As things are changing in what they call the genesis areas. It's to do with wind shear. I don't know if you've been, paying too much attention to the expectation that we'll have a strong El Nino this year. That's looking very likely. And the forecast for hurricanes is that there will be fewer hurricanes in an El Nino year. That's very well established. So the story is and I try to talk about it in the book, and I explain why, that there will be fewer hurricanes overall, but a greater number of very intense ones.
Professor, the book dedicates significant space to how climate predictions are made and the sources of uncertainty in forecasting. For non-scientists, uncertainty is science often gets misread as we don't know. How do you explain to a journal audience that uncertainty in models doesn't mean unreliability? And why does that distinction matter for policy?
Yeah, so the models will always be somewhat different. Um, Nobody thinks that there is an ideal model. Nobody thinks that of all the models that are out there, one of them's going to win. That's probably not going to happen. Uh, the analogy I use sometimes is that, you know, if you're searching on the internet to try to find some information, you can go to half a dozen different search tools and you'll get slightly different answers. Now, is one answer correct and the other answer is wrong? The answer is no. We don't know which one is correct and which one is wrong. They're all equally wrong. They're all not precise, but they're not precise in different individual ways. Um, the greatest uncertainty in the future is not in the models. It's in the input to the models. The models need to know what the CO2 concentration in the atmosphere is going to be in the future. And that's not a science problem. That's a political problem. People are going to pay attention to the fact that we know that carbon dioxide in the atmosphere has the effect of increasing the average temperature at the surface. So we know that happens. There's some uncertainty in it, but the greater uncertainty is trying to understand how societies will behave in the future. Will we keep emitting? Will we take electric vehicles seriously? Will we try to stop generating electricity with coal? And that's a political decision. And different countries are making different decisions. So overall, emissions are increasing because there's enough countries are still burning coal, and I think India is still burning coal. So is China, so is the US, and other countries have made strong commitments to move to renewable energy sources like, you know, wind and solar. And it's clearly being demonstrated now that wind and solar are viable. They can produce enough electricity for our needs. We don't have to fall back on coal. And geothermal is interesting as well, but we don't need, there's no requirement that we burn coal to create energy.
Professor, one of the major updates in the second edition is the inclusion of attribution science, the ability to determine how much of a specific extreme weather event was caused by climate change. Can you walk us through a real world example where attribution science has been used and how it's beginning to reshape legal and humanitarian accountability framework?
Yeah, so when I wrote the first edition of this book, I didn't know there would be a second edition. I thought there'd be only one. And I didn't address attribution science because at the time I didn't know enough about it. And I wasn't prepared to write on a subject that I don't understand myself. Now, in the 5 or so years that have passed, I do understand it a bit better. And it's a question of statistics and probabilities. Unfortunately, you will see the press sometimes saying there was a big cyclone because of climate change. That's not correct. Cyclones, big cyclones, are going to be made more likely, more probable by climate warming, but they are not caused specifically. You cannot say this particular cyclone happened because of climate change. You can say it was made more likely by climate change, but not caused by climate change. And that's the big difference. And I now understand enough about statistical probabilities that I know what you should say. I correct people all the time. I write to newspapers. I tell them, no, you've said the wrong thing. It doesn't make a lot of difference, it seems. Some people thank me for trying to correct them, and other people don't want to be corrected. They don't like being corrected. So and do my best. And now I think I do understand enough about it to write a couple of pages on it. It's not very extensive, and the field is very, very large. It's getting better. The statistics of changing likelihoods is getting stronger and stronger. And fortunately for us, the statistics are well established. This is not, it doesn't require new statistics. It requires us to apply commonly known statistics to a particularly tricky problem, but it doesn't require new statistics.
Professor, the second edition adds an entirely new chapter on geoengineering, from solar radiation management to direct carbon dioxide removal. Personally, where do you stand? Is geoengineering a legitimate safety net, or does it risk becoming humanity's more excuse to keep polluting?
Yeah, so it's again, the reason I included it was not because I didn't understand it. It was because, this is called climate change science. And I wasn't sure whether geoengineering is a science or it's something different. But I think it's important enough now that I have to say things about it, which again, uh, primarily factual, um, and not my opinion. But so let me say my opinion, if you want to hear it, is that I would rather we didn't do any geoengineering, but I think we're going to have to. I don't think we've got any choice in the matter anymore. And a number of people have changed their mind from saying that you must never do geoengineering to say it's too late. We're going to have to. The deliberate intervention in the climate system makes people very nervous. It makes me nervous. But we have already intervened in the climate system. We've made the temperature rise because of the emissions into the atmosphere. It's too late. We've already done it. And it's becoming more and more urgent. So doing something in geoengineering, I think, is required. And what I think that the wisest people say is that we should be doing controlled experiments, little experiments, a little experiment with solar radiation management and see if it works and see how large the effect is. So let's say we put some particulate matter like uh, sulfate into the atmosphere. We don't know right now how much the temperature will change for a certain amount of sulfate. So if I put 1,000 tons of sulfate in the stratosphere, how much will the temperature change? We don't know that. It may change a lot. It may change more than we want it to, okay? And it may influence the repairing of the ozone hole. It might. There's physics to suggest that it does, but we don't know until we do an experiment just how much it will change the temperature and what the side effects might be. It's dangerous, I think, because we don't know enough about it to really be confident that we might overstep and do something that has very negative consequences. Now, with sulfur in the atmosphere, stratosphere, it's it might be okay because it doesn't stay there very long, a couple of years. We know that from volcanic eruptions. So even if we do something that we didn't intend, it will repair itself after a couple of years. They might be miserable years, but it isn't like it can run away and go terribly wrong for a long time. The thing that I'd like to think is going to help a lot is what's called direct air capture. That is not trying to prevent carbon dioxide from coming into the atmosphere, but trying to remove what's already there. That can't go wrong, right? An experiment in direct air capture can't have a bad consequence. It either works or it doesn't, right? And right now, it's not working as well as it needs to be in order to make a difference, but it's not causing any harm. And there's no likelihood that it could cause any harm. But if you think of things like fertilizing the ocean and messing with the stratosphere, all sorts of bad things could happen. So you need very, very limited experiments, prototypes to see what might work and might not. Sorry.
Professor, solar radiation management, the idea of reflecting sunlight away from Earth, sounds almost science fictional. But who governs these interventions? If one nation decides to act unilaterally to cool the planet, what are the risks for the rest of the world?
Well, that's the thing, and you've got that exactly right. If some rogue nation decides to use its aeroplane fleet, its air force, to go up into the stratosphere, which we can, and dump a lot of sulfur out there, you can't keep it in place. It's going to spread around the whole world. That's the nature of the stratosphere, as opposed to the troposphere, which is what we sit in. The troposphere has weather. You know, it's got convection doing this and a cyclone doing that, and winds doing this. You know, you can isolate something in the troposphere, but you can't isolate something in the stratosphere, the next layer above. Okay, so it'll spread over the whole world. We know this from observations of volcanic ash that have penetrated the high atmosphere and the stratosphere, and we've seen temperature drops for a couple of years associated with them. But it doesn't give us a quantification. It just tells us that if we put this material into the stratosphere, the temperature below will drop. Now, that does nothing for CO2 emissions. It doesn't change the emissions at all. It just puts up an umbrella to shade us from the sun. That's all it's doing. And it could have a lot of unintended side effects, but I think that the engineering of it is highly plausible. Aeroplanes can fly at the level of the stratosphere. Big aeroplanes could dump all sorts of material. Weather balloons routinely go up into the stratosphere and could be equipped to release carbon dioxide. As an engineering challenge, I think it's very doable. And that's in a way, that's what's a little bit scary about it, because it is doable and there is no international regime that would prevent any rogue nation from doing that if they wanted to.
Professor, this book is explicitly written for students of sustainable development, not just climate science. In your view, what does a development economist or a public policy student gain from deeply understanding climate science that they simply cannot get from policy report or IPCC summaries alone?
Yeah, so I think, and I've been told, that this little book is, it was written for undergraduates and master's students because of my teaching. Okay, it's a supplement to my teaching. I tell students this is the book, You should know everything in this book. And it doesn't mean you don't have to come to lectures. And that's the way it's interpreted by some students. Say, well, buy the book, I don't have to come to lectures. It's written in a way that is meant to engage more than just students. And I know that there's a number of professionals who work in climate adaptation policy, things like that, who don't have any background in the science. They just accept the science, but they don't understand how to evaluate it. So it tries to do that. It tries to provide the essence of what everybody should know. Is that what you were asking?
Yes, Professor.
Yeah. Yeah.
Professor, I would like to conclude this episode with one final question. The second edition incorporates the latest IPCC assessment report. The
Yep.
IPCC process is rigorous but very slow, and the climate system is changing faster than reporting cycles. Do you think the IPCC model of scientific consensus building is still fit for purpose in an era of accelerating climate disruption? Or does the world needs a faster, more responsive science to policy pipeline?
Yeah, so there's two things. You're absolutely right. I think the IPCC process is too slow. All sorts of conclusions leaked along the way. So by the time these reports come out, and I already know what's in them because everybody's talking about them. So it's a strange process in that way. And it's a process that's run by scientists when in fact it's more than a science problem. And so you get this so-called summary for policymakers. Well, it's what scientists think policymakers should know. It's not what policymakers are asking to know. It's what we scientists think they should know. And in that way, it doesn't always help because it isn't always what policymakers need to know, and they need to act quickly because bad things are happening quickly. So the IPCC process has been very helpful, but if you could give a yearly update instead of something that comes every, what is it, 5, 6, 7 years, the updates have to be sooner than that. They have to be on a faster schedule. Now, I think we can do that. There's no reason to be as slow as what's happening. In a way, the reports are too comprehensive. They try to examine every corner of the science, which is probably not necessary. We need these updates more often, and there's something called CMIP, which is the Coupled Model Intercomparison Project, in which you put together a lot of different climate models with the same input, and they'll give you different outputs. So they try to figure out why the models are giving different outputs, okay? In the way of trying to home in on what really is the best model, okay? The CMIPs come out once every 7 years. 7 years. And things have changed so much in 7 years. So we need a process that can accelerate what the IPCC does and what CMIP, the coupled model intercomparison process. It has to happen faster. You're exactly right about that.
Professor John Mutter, this conversation has been a masterclass in seeing climate change not just as a scientific challenge, but as a mirror held up to society's deepest inequalities. Thank you for making the science accessible, urgent, and deeply human. For our listeners, Climate Change Science, a primer for sustainable development, is now available, and I cannot recommend it enough as your starting point for understanding the world we are inheriting. Thank you again, Professor John, for sharing your time and fascinating publication with us today. This has been a truly enlightening. Thank you so much.
Thank you. I really appreciate you wanting to talk to me. You are in a part of the world that is going to suffer considerably So it's very right that you should be asking questions about this and learning. You don't have to know the science from soup to nuts. You don't have to know everything. You just have to know a core canon, basically. And that's what I've tried to do.
Thank you.
Thank you.